So in 6.5, we're going to cover the concept of impulse and the Dirac delta function. I forget how you pronounce his name correctly. But the basic principle of this, and this is a very challenging section because this function isn't a traditional function. That's the first thing you have to understand. Like this isn't like f of x equals x squared. Like this is a weird function, quote unquote. It's not even like a regular function, right? That is very useful in a particular situation of us wanting to represent something happening very quickly, um, but there being a lot of it over a short period of time. And the most common example is imagine you're striking something with a hammer, or a bullet is hitting a block of wood. The bullet hits the block of wood, very quickly and disperses all of its energy. The moment that happens is very short. So it's kind of hard to represent that as a normal function because if you were to look at it over entire domain of, negative infinity to infinity of time, the moment it hits, it's like instantaneous, like it's very short. So that's the power of this function. It allows us to represent these large forces over a small time frame, right? So that's the basic principle because if you were to imagine, so like I said, imagine a large force at a moment in time, it would look like this. Force time. Basically, it's zero. And then all of a sudden it's all the way up here and then it's zero again, right? Like that's really what happened. It was zero, it went up, and then it went down. How do you find or how do you work with that, right? Like how do I convert that into something that's useful? Well, that's where this idea of impulse and, the delta function comes into play. Basically, what they say is, okay, at this current zoom point of the function, I don't see anything. All I see is like this, a straight line, and that. Like that's all I see. Okay. But what if I zoomed in? Like imagine you zoomed in and you zoomed in so much, like milliseconds, nanoseconds, right? Like you zoom in so much, effectively what you get is this. You're now at a level that is so small in terms of how much you're moving to the left and right that your function could look like this, right? Where this is the moment at impact, let's just call it A, and then right here it's like A minus a little bit, which we usually call epsilon, and then A plus epsilon, right? Like that's what we're doing, is we're basically analyzing what's happening here. Now, is it going to be a curve like that? No, probably not. This is more of like a normal distribution type thing. What it could look like is maybe like a box, like, right? Like it hits it and then it stops. And the question is, A, well, what's this epsilon number, right? Like, what does that mean? Like, how do I know what it is? The truth is, it's just going to be a really small number. And then what's the value of this curve at this point? Like, what is f of a? That's my question, right? Like, what is it? These are all questions that you can think about. Maybe another question is, well, what's the area under the curve, right? Like, is there an area? Because clearly, if I look at the picture above, there is no area. It's a straight line. So there's a problem there, right? And so this mathematician, Dirac, or however you pronounce it, I know I'm mispronouncing it probably, he came up with this idea of, okay, we're not going to think about this in the traditional sense, right? So um, this function is not really a traditional function, but rather a distribution. That's really what it is. It's a distribution, or we call it a generalized function, right? And so, depending on how much you zoom in and zoom out, it'll change the shape of the curve, but we have some very important properties that we establish so that way we can kind of maintain this idea of it behaving no matter how we're looking at it, right? And so the next three things that I talk about, they are like where they come from is very difficult to really explain. You have to kind of go beyond the scope of this class. But these are just three properties that we're going to establish with this delta function. Okay, so the Dirac delta function. And at the end of the day, in this class, just understand the big picture. This is a nice function that can represent a really big number or an infinite value, quote unquote, in a very short time span. And it's just very good at representing engineering problems where I just need something for a brief moment. Like I said, like a circuit turning on or a bullet hitting a block or a hammer hitting a wall, something like that. Like it's very quick. And that's all I want from it. So the delta function is defined as, and so this is the notation that we're going to use. Uh, See if I remember how to make a delta off the top of my head. So delta t minus a, where it satisfies the following three properties. At the end of the day, do you need to memorize these three properties? No, you really don't, but they are important to talk about for a brief second. So the delta function is equal to 0 if t does not equal a. Okay? So anytime you're not at a, the function's 0. Nothing is happening. If you integrate the delta function around a, so a minus epsilon and a plus epsilon, right? You're within like a is contained in the interval, then the integral has an area of 1. Okay? And then number 3 is in similar fashion. If you take the integral of a minus epsilon and a plus epsilon of the delta function times f of t times delta t minus a dt, then this is just equal to, well, we know what the delta function is, it's 1. So then this is f of a, right? Now there's some convolution aspect to this, but you don't need to worry about that. So if I'm applying 20 pounds of, force when I punch like a punching bag, that brief moment I hit the bag is 20 pounds, right? And then every other time it's 0. So that's what that F of A is. It's just how much force I applied at that exact moment I, hit it. You could think about it this way, right? When you strike something, the object hitting the other object, they are connected for, it's not an instant, I touch it and then not touch it anymore. It's touching it for, like a couple, microseconds or whatever, and then it untouches it, right? So you can think of it that way too. That's what the epsilon is, like that brief moment where it's still in contact. So that's a delta function. It's just this very special function that allows us to represent us applying some kind of, value at a quick moment. And in the context of this class, the only thing that you really need to remember is just what is the Laplace transformation formula, and then how do I do the inverse Laplace to get back to it, right? And that's it. That's all it comes down to. It's just being able to do that. So, Laplace transformation. Now, thankfully, it's not a difficult formula, right? So, the Laplace transformation of the delta function t minus a, delta is not very good, is equal to, and it will look vaguely familiar, e to the negative as. So it's basically like the step function. Oops, sorry, wrong one. Just without the s dividing it. So a is positive. That's it. That's the Laplace transformation. And that's all that's really going to come down to is you not even remembering that, just knowing which one this belongs to, which on the table will be provided. So with that, we're going to be able to solve a differential equation using this type of function now. So that's going to be our next example. Solve the IVP y double prime plus 16y equal to 8 times the delta function t minus 9, given the initial conditions y of 0 equals 0, y prime of 0 equals 0. So, step 1, formula. Write down whatever formulas you need to. I'm going to always write this one down because this is, again, the most important one in my opinion. You're not going to be given this formula directly on the exam. You'll be given the generalized version where it's like, with all the derivatives on it. So you kind of have to be able to read that or just memorize it this way. Again, no y prime. If you're wondering, why don't we have y prime in any of these examples? For the sole fact that it just makes the multiplication a little bit more complicated. So in turn, this just makes it a little bit more digestible with these examples. But if you add a y prime, it just makes it a little bit longer, makes the partial fraction decomposition a little bit more difficult. But beyond that, it's not any more conceptually more difficult, just computationally more difficult. Step 2, we're going to take the Laplace transform both sides. I don't have to do any conversions to it. So the Laplace transformation of y double prime plus 16 Laplace transformation of y equal to 8 Laplace transformation of the delta function t minus 9. Just like before, you could also probably write it like this. Like put the a as a subscript. That's perfectly valid. Whatever makes you happy in that respect. All right. Step 3 is we're going to evaluate and initial conditions. So s squared y of s minus 0 times s minus, actually, I'm skipping a step, aren't I? Y of 0 minus y prime of 0 plus 16 y of s equal to 8 e to the negative 9s. If anything, that feels a lot easier than what we've been doing before. S squared y of s minus s times 0 minus 0. So the delta function is intimidating for sure. But in terms of a computational aspect, that's actually not bad at all. So we got that, and now we just want to isolate y of s. So y of s times, nope, that's incorrect. S squared y of s, all of those became 0, so minus 0 minus 0 plus 16 y of s equal to 8 e to the negative 9s, correct? Yep. And so s squared y of s plus 16 y of s equals 8 e to the negative 9s. And then y of s times s squared plus 16 equals 8 e to the negative 9s. And then y of s is equal to 8e to the negative 9s over s squared plus 16. And from that, we're going to do the inverse Laplace. So, well, actually, we got to think about this. Do we need to do completing the square, partial fraction decomposition? So step 5 is a PFD or complete square, if necessary. Better word, needed, because I can spell that. Well, I see s squared plus 16, so I mean, I could try doing partial fraction decomposition. But we think about it and we realize actually that's just sine, if you think about it, closely. So not needed. So we don't need that. And then step 6 is inverse. So the inverse Laplace of y of s is equal to the inverse Laplace of, I don't know, 8e to the negative 9s over s squared plus 16. So we got to think to ourselves, okay, I have s squared plus 16, right? So whenever you're dealing with exponentials and other functions, I think it's not a bad idea to separate it and make it look like this because it makes it more obvious what you're trying to do, right? Notice that it's e to the as times a function, right? Like it's a function. And so we just think to ourselves, okay, this looks familiar. And then I scroll up to my table and I look for one that has e to the negative as in the answer, and I see it right here. E to the negative, they use c, but as times f of s. F of s is just the inverse Laplace, or sorry, the Laplace transformation. So this is e to the as negative, and this is f of s, right? And so the what's it called? The inverse Laplace is just going to be, right? If you go backwards, so the inverse Laplace of e to the negative as f of s, well, that's just going to be equal to the step function at a f of t minus a, right? Going from inverse back is sometimes more difficult because you're basically undoing something and your brain likes to go forward, not backwards with that kind of stuff. So essentially, we're going to do the step function at t minus 9. And then we know, if you notice that 8 is really just 4. Well, actually, you know what? I'll show that step. The Laplace transformation of e to the negative 9s times 4 times 2 over s squared plus 4 squared, like that. And then now I have the 4 right there, so I could factor out the 2. That's 4 squared. And then this is going to be equal to 2 step function t minus 9. And then this is sine of 2t, right? However, I have to shift it over. We'll do t minus a. And so this is equal to 2 step function t minus 9 sine of 2 times t minus 9, like that. Forgot the minus sign. And there's the answer. And that's the delta function. Except it's not 2 because it's 4 squared, so it should be 4. Silly mistake on my part. It's 4 squared. I was thinking I saw the other 2, so I wrote down 2. So very easy to make that silly mistake. But that's delta function. Again, how do I make this more difficult? I just make the numbers nastier. That's really all I can do. I make it partial fraction decomposition, so then that just becomes a little bit nastier. So, I mean, that's kind of the huge difference. But overall, that's the delta function. Now, if you're wondering, like, what do these graphs even look like? If you were to graph something like this, and I'll show you on the next slide. So from Wolfram, that's what it would look like. So for the first 9 seconds, it's just a homogeneous differential equation is equal to 0. And then right when it hits it at 9, it activates. Now, I just realized that, what's it called? Wolfram is calling that the Heaviside function. We don't want that. Actually, no, we do. Sorry, I was thinking something else. But yeah, that's what it ends up looking like. So that's kind of the behavior that the curve is going to have essentially once it's been activated. So you can think of it that way. Like this system would do nothing forever, but at 9 seconds it hits it, and now it's going to behave like this because of that hit afterwards. I want to be clear on the differential equation we solved was a y double prime plus 16y, which means there's no damping. So essentially, the system receives energy and then it's not removing it at any point. Now, if you were to solve a differential equation that did remove energy, then it would start to decay over time. So I can quickly make a picture of what that would look like where we add a decaying factor to it. So let's write that down. This is where we have something like y double prime plus 16y prime equal to, delta t minus a. There is no decay due, oops, to y prime being equal to 0. So here's the picture where we add decay essentially, or friction. So y double prime plus, in this case, this was 10y prime plus 29y equal to delta function t minus 2. And then because there is decay, you get that initial burst and then it comes back down. So there is decay after t equals 2. If you add a forcing function to the delta function, then it'll have like that steady state where it levels out to a specific value or behavior in the long run. But that's the delta function.